All right, so chapter number 7 is a good one. Chapter number 7 is all about periodic trends. It goes into what individual atoms look like and everything like that. So, periodic trends, that's really just a catch-all term for when you look at the periodic table, what informa what information can you extract from it? So, one thing that you can do is you can look at the periodic table and it's organized in a way that gives you that's a little bit predictable. So moving across the table left to right and up and down, well, that gives you some insight into what an element or how an element behaves. We started the semester when we talked about metals versus nonmetals, and then we talked about the different classifications. At this point, we've talked about number of electrons around an atom, and now what we're going to do is we're going to investigate that a little bit further. So one of the things that you need to understand about every single atom is this concept of an effective nuclear charge. So when you think about that, and when you think about the effective nuclear charge, it's important to remember the structure. So we have a nucleus, and then let's say that we have, let's just say 6 electrons. Well, the first two are going to be right here, the next two, and these first two are going to have the sense and basically the pull of all of the protons that are in that nucleus. Okay, now the next sort of orbital, we've got 2 more electrons. Okay, and then when we go beyond there to place our 5th and our 6th electrons, well, those all of those electrons are going to be attracted to the nucleus because the nucleus has your neutrons and your protons. All of these electrons are negatively charged. Now, do all of these electrons experience the same force from that nucleus? And to put it simply, the answer is no. Why is that? Well, think about these electrons right here, the ones that I've underlined. Those 2 electrons are the closest to the nucleus. So it's kind of like these electrons right here. What's the pull that they're going to feel from this nucleus? They're going to feel the sensation of being pulled by 6 protons. Okay, well now if we go to this next realm, I'm going to change color and I'm going to go to orange. These next 2 electrons, well, are they going to feel the exact same force or the same attractive force as the first 2 electrons? And the answer to that is no, because of the fact that these inner 2 electrons, this one and this one, what are they going to be doing to these that I've just underlined? Well, they're basically going to be shielding. And so we use this term ZEFF, Z sub EFF, or the the effective nuclear charge, in order to take that into consideration. So Z sub EFF is the effective nuclear charge. And sorry for my random writing there, but that effective nuclear charge looks at the total number of protons in a nucleus and subtracts the screening constant. The screening constant represents the portion of the nuclear charge that is screened from the valence electron by the other electrons in the atom. So if you take something like this outermost electron right here, these outermost electrons out here, well, they're going to be screened by all of these 4 electrons on the inner rings. So that's just something to keep in mind, that Z sub EFF takes into consideration all of the different kind of inner shell electrons that are going to kind of be blocking the force from from the nucleus. Now, the positive charge, essentially what that means is the positive charge experienced by outer shell electrons is always less than the full nuclear charge because the inner shell electrons partially offset the positive charge of the nucleus. Okay, now whenever you start talking about basically individual atoms, you can think about the number of neutrons and protons in the nucleus as well as the number of electrons in those outer rings. And you got to keep in mind all the different forces at play. We've talked a little bit about organization of all the electrons surrounding an atom, but now we're going to go into it a little bit deeper. Okay. So whenever it comes to atomic radius, within each group, so keep in mind a group is going to be the going up and down, so the columns on the periodic table. the atomic radius tends to increase from the top to the bottom. So atoms at the top are going to be smaller than atoms at the bottom within a group. Okay, within each period, so moving left to right or right to left on the periodic table, the atomic radius tends to increase moving right to left. Okay, so on the right-hand side, your non-metals down to the metals, or sorry, non-metals over to the metals. So essentially what that rounds up to is, when you look at the overall display of the periodic table, your largest atoms, the largest atomic radius is going to be in that lower left-hand corner. So if you take an atom like Fr, for instance, francium is going to be large compared to something like fluorine. Okay, so yeah, lower left-hand corner, biggest atoms. Okay, we see that same sort of thing here. And now what this shows us is an approximate measure of these. Now, these are all measured in the units of angstroms. So your largest atoms, the one that's largest here on this table is rubidium Rb. Rb is 2.11 angstroms compared to your smallest atom of helium, which is 0.32 angstroms. This is our abrupt pause. Please continue on in the next video. Have a good one.